And it's time to play with patterns. So there's infinitely many types of patterns out there. Some patterns are, uh-oh, my tablet is having a hard time connecting. Oh, it says it's connected. Oh, its battery is low again. Hopefully we'll get through class. Patterns, uh-oh. Patterns, there we go. Mostly what we're looking at number patterns, but it could be patterns in geometry. Oh no. And numbers and geometry, and I'm gonna have to go get a charger. Give me one moment. So the patterns are often gonna stem from the counting numbers. Most of the patterns that we see are going to have a first thing and a second thing and a third thing and a fourth thing and so on down the line. Counting numbers are also called the natural numbers, which we'll play more with. And so often what we're trying to do with these patterns is just predict what comes next, and can we describe that pattern somehow that someone else can understand it. Suppose I started off with 2, and then 5, and then 8, and then 11. So my first number is 2, my second number is 5, my third number is 8, my fourth number is 11, and then I want to try to continue this pattern. And there's lots of different ways patterns can continue, and it turns out for any particular pattern, there's usually more than one logical way you can continue the pattern. This one, I think, has a pretty logical way to look at. When I look at these numbers, I'm seeing that they are 3 apart. And I should just keep counting 3 apart. Now that pattern right there isn't as obvious as, say, the pattern 0, 3, 6, 9. These numbers are also 3 apart. And I'm hoping to continue that pattern. But one thing that's true about both of these patterns is they have what's called a common difference of 3. Not all patterns have a common difference. And we saw some of those last time. We'll look at some more today. So continuing the red pattern, I think that next it should be 11 plus 3 or 14. 14 plus 3 is 17, and so on down the line. And then I want to find a way to identify future parts of this pattern. Like I might want to be able to identify what's the 12th number in the list, maybe the 100th number in the list. To do that, I got a couple of choices. I can either keep counting by 3 till I get to the 12th one and counting by 3 till I get to the 100th one. Be a little tedious, but I could do it. A spreadsheet would help me get there quicker. Or I could try and find a formula where I just plug in 12 and out pops the answer. Plug in 100 and out pops the answer. Now, when we do that, to plug in, that means when we plug in, think back to like your algebra days, that means you have some place to plug into, some kind of variable to use. And usually when we're counting, we use the variable n as our counter. So for example, the term 17, its n would be 1, 2, 3, 4, 5, 6. It's the 6th number. So I could say if n equals 6, the result should be 17. And oftentimes we'll give that result a name. And so think back again to your algebra days, you had equations that you played with like y equals mx plus b, where x was a variable and y was a variable, but m and b were some special numbers that you plugged in. Okay, so for example, we might have something like y equals 3x minus 1. And then somebody says, okay, well, x is 6, and we would plug in 6 and tell somebody what y is. So we want to do something similar to this, but instead of an x, we're going to use an n for that formula. Now I'm going to take the 369 out of here for a moment. We can come back to that one. And I have that common difference there. Oops, didn't mean to erase that. So how do we figure out how to extend the pattern? Well, we clearly have one way. Anybody can continue this pattern by adding 3 over and over again. But again, none of us really want to get the 100th one that way. So the thing to notice is these repeated 3s. And maybe you'll remember from your early days in mathematics in elementary school, after you learn to add, you learn that repeated addition was this idea called multiplication. And so if we pick on the number 17, for example, to get that number 17, I had to start with the 2, right? So I started here, and then I added 3, 1, 2, 3, 4, 5 times to get to that 17. So let me just double check that with a little arithmetic. So my claim is that if I start at 2, and then I add 5 3s, I should get 17. All right, well, let's see, what's 5 times 3? On a good day, it's 15. 2 plus 15 is definitely 17. So I can rewrite this repeated addition to make the problem a little easier to write down. So now if I can only figure out how many 3s I need to get to the 12th one, or how many 3s I need to get to the 100th one, instead of adding 3 again and again, I can just do a quick multiplication and I can get there. So let's break that down. So a lot of times when I'm working with patterns, I write it down in different ways, hoping my brain can discover something. So often I will write it in a vertical table where I have n. And earlier I mentioned we used to use y's and x's. A lot of times when people are working with sequences, they name them things like sequence A and sequence B. So we can do that. I'll show you another trick with that in a moment. So let's say sequence A are the numbers we had there, which were 2, 5, 8, 11, 14, and 17. And the 2 is the first term, and the 5 is the second, and the 8 is the third, and 11 is the fourth, and 5th is 14, and the 6th one is 17. And what we want to do is ultimately, we want to find a connection, a way to connect the number 2 to the number 5, a way to connect 3 to 8, a way to connect 4 to 11, and so on down the list here. And I'm going to do that with the add 3 thing. So looking back at my work here, to get to the 5, I started with 2, and then I can add 3 to get there. So I'm just going to make a note of that in my table. The 5 came from 2 plus 3. And then to get to the 8, we just added another 3. So the 8 was the 2 plus the 3 plus one more 3, right? Here's the 5 there plus the 3 gives me the 8. And I just kept putting 3s on there. So the 11 must be 2 plus 3 plus 3, and then one more 3. And each time we get an extra 3 there. So let's write this in a slightly different way. To get to the 5, I started with 2, and then I added on 1, 3. To get to the 8, I started with the 2, and I had to add on 2 3s. To get to the 11, I started with 2, and I got to add on 3 3s. Okay, and hopefully we see a pattern here. There's always a 2, and there's a bunch of 3s. 1, 2, 3. So the 14 must be 2 plus 4 3s. And the 17, we already saw that. Excuse me, my pen is or my hand is helping my pen glitch, 2 plus 5 threes. And again, I'm trying to find a connection to the number I started with here and a pattern over on the other side. And what I see is this 2 and then a 3, right? That's changing as I go down there. What's changing over here is the 1 and the 2 and the 3. And if I take that back one step, then the 2 here must be 2 plus no 3s. And so what I see is that the number over here, the 0, the 1, the 2, the 3, it's always 1 less than the number I started with over here, right? The position I'm at. So I'm just going to make a note of that. This is always 1 less than the number I'm calling n. All right, so I want a formula that has n in it, and I've almost got it. I have a formula that has 1 less than n. And so mathematically speaking, the way I would write that down is just n minus 1. Take a number, whatever number it is, subtract 1, right? That's 1 less than whatever n is. So here's what I think my formula is based on this. Starting with 2, add parentheses n minus 1 times 3. And I want to just point out the n minus 1, why it makes sense if I look back at the previous example. 2 is where I'm starting, right? To get to another number, I have to jump over. So there's 1 jump to get to the second number. There's 2 jumps to get to the third number. But I'm already at the first spot. To get to other numbers, I just count how many jumps I make. And I'm always going to make n minus 1 jumps because I had to start at position 1. We're going to look at this another way to see how it makes sense. So that's one way to come up with the pattern. And I can test to see if this works by just plugging into it. So I'm going to check it. So we're going to check by picking a number we know. So I know one of the originally given numbers was the third one number was 8. So I'm going to check for n equals 3. And I'm going to plug into my formula. So the value for a there is going to be 2 plus parentheses. Instead of an n, I'm going to put a 3 minus 1 times 3. 3 minus 1 is 2. 2 times 3 is 6. Plus that 2 I started with gives me the 8. So the formula does check for n equals 3. Usually I'll check for another number just to make sure, but we have a pretty clear pattern here. As long as we're confident we wrote it down there right, we should be good. But it's a good idea to check it for at least 2 numbers that you were given before you proceed. So now I have a formula where I just can plug in 100 and get the 100th one. I want to look at this just a slightly different way. And this is kind of what I did last time and in some of the other videos. So my pattern again was 2, 5, 8, 11, 14, and then 17. And we got that pattern by adding 3 repeatedly. And we made the note that repeated addition is multiplication. And so from here, I could just say, all right, then I know my answer, and I was calling these the A values, the A's, that A has to have something to do with 3 times n. And remember, n is my counter. So up here, sometimes I like to write those in too. N is 1, n is 2, n is 3, n is 4, 5, and 6. So this is my guess at the formula because I have the repeated 3s. So guess. Next, I'm going to check it. So if n is equal to 3, for example, then I think that A is equal to 3 times 3. 3 times 3 is 6. What do I want it to be? I want it to be 8. Okay, I'm close. It's got to be times 3 because the repeated 3. So I'm thinking I can just tweak this here. How can I tweak it? I can tweak it by adding 2 because I really want the answer to be 8. All right, so I did a guess, check, modified my guess. So this is like my problem solving procedure, right? I try to understand the problem, I'm making a plan, checking my work. I'm modifying my strategy. So now I'm going to check again. Let's pick n equals 4. I think my formula is now 3n plus, 2, based on my guess and check. So now we try it. For 4, a should be equal to 3 times 4 plus 2. 3 times 4 is 12, plus 2 is 14, and ooh, that's not right. I did something wrong. Oh, you know what I did wrong? Wait, did I do something wrong here? Oh, yeah, what did I do wrong?
You did 3 plus 3 equals 6 when it equals 9.
3 times 3 is 9. Oh, don't you hate when those things happen? Thank you for straightening me out there. All right, so let's fix my guess and check. I added when I should have multiplied. Let's see, I was using red at first. Okay, so 3 times 3 is really 9. I wanted it to be 8. All right, so I'm going to take away 1. So let's get rid of those pluses.
I mean, technically, the 3 plus 3 plus 2 would have been right for number 11.
Yeah, right. But I'm trying to match up, right? N was 3, and that's there. Yeah. So yeah, the number was in the list. I was just looking in the wrong spot. Okay. So, and I multiplied wrong. So we want to do a -1 on that to get 8, which means there should have been a -1 there and a -1 there. Okay. Let's check it properly. We have 3 times 4, right? 4 is my n. And then -1. 3 times 4 is 12. -1 is 11. That looks better. Cool. And this is why I mentioned before, I usually check more than once to make sure I'm getting it right, because sometimes I do silly things, like say 3 times 3 is 6, when it really should be 9. All right, so now I think it's, I have the right formula. So I think the formula is 3n minus 1. And if somebody says, what's the 100th term? I can tell them by just plugging in 100, which is kind of neat. Other things I can do is somebody can say, hey, is this number in your list? So that'd be kind of a problem solving thing. So let's try that, and then we'll move on to a new problem. So here I'm saying my A's are still the 2, 5, 8, 11, 14, and so on. And then someone asks, is 151 in this list? Well, if it is, then I should be able to figure out what value of n gets me there, right? So remember, we always have a counter. 1, 2, 3, 4, 5. If somebody asked me if 7 was in the list, what would you tell me? You would say, no, 7's definitely on the list. We go from 5 to 8, 7's in between, it ain't in the list. But I don't have the list shown up to 151. So I do know that to calculate an A, I just take 3 times whatever n is and subtract 1. And if I knew what n was to get 151, I would just plug it in, but I don't. So instead, what I'm going to do is I'm just going to say, well, let's set it equal to 151 and see what happens. All right, so now I have to solve this. So to solve this, what would I do? I think I would add 1, -1 plus 1, that goes away. So I have just 3n on that side. On the other side, I have 152. This is a multiplication, so to undo that, I divide. And so 3 over 3 is 1n, or just n, and then I have to take 3 into 152. So I'm just going to whip that out on the side here. Calculator's often helpful. 3 goes into 15 5 times. 5 times 3 is 15. Subtract, bring down the next number. 3 does not go into 2, so that's the remainder. Wait a minute, you can't have a remainder. N's a counting number. It's either 50 or it's 51. It's not 50 and a little bit. So what I found here is that 3 went into 152 50 and 2/3 times. Uh-oh. So the answer is 151 in this list? The answer is no, because I'm not getting a counting number there. what number would be in this list? Well, since there's a remainder of 2, right, I'm a little bit off. So how about if we, let's see, take 2 away from that, that would give me what, 149? I think 149 is in this list eventually, because my claim is that gets rid of the remainder 2. Check it out. 3 times 50 minus 1, right? That's my formula, is 150 minus 1, or 149. Yeah, so 149 is the 50th number in this list, is what I found there. So 149 is in the list, 151 is not, because I got a fractional number and the number has to be counting. 1, 2, 3, 4, whole number. Okay. One last thing about this problem, and then we'll move on to another one. I know I said that already, but we have 2 different formulas for this. I took one approach for this and found that the formula for the A's was equal to 2 plus n minus 1 in parentheses times 3. And I found another formula that said the A's are actually 3 n minus 1. And it turns out they're both great formulas. They describe the situation in different ways. And you should see that the first homework problem for section 1.2 goes over a system like this where different students saw something different and came up with different formulas. But the bottom line is there should be a way to connect these 2 together. And when I look at this formula right here, if somebody said, can you write this formula here with less ink? I would say no, because the 3 and the n are stuck together with multiplication. And until I know n, I can't continue. But up here, it turns out I can clean that top one up. This one here does reduce. So let's take a look at how. Whenever we multiply by a parentheses, we have the option to distribute. So then I can view this part right here as 3n minus 3, right? 3 times 1 is 3, minus is in between, 3 times n is 3n. 2 is hanging out front. Now the 3 and the n are stuck together, but this 2 without a variable and this negative 3 without a variable, I can work on those together. So I could rewrite this to say this is really 3n minus 3. I can put the plus 2 over here because it doesn't matter what order you add. And then if I have a loss of 3 and a gain of 2, that means altogether I'm just down 1. So there's my 3n minus 1. So it turns out I can use less ink to use the first formula, meaning it's going to give me the same results as the second one.